Hi. First of all, thank you for showing interest in my work. My name is Gerald Drenthe, and I will talk about my work titled DTI reveals altered structural connectivity of pain-associated regions in a genetic variant of small fiber neuropathy. I have nothing to disclose. Small fiber neuropathy, or SFN, is a neuropathic disorder associated with chronic pain. Around 5% of the people with SFN harbor a mutation in the SCN9A gene. We refer to this as the genetic SFN. Chronic pain may lead to changes in the brain, for example related to morphology but also to the structural network. Therefore, in this study, we would like to investigate what the potential effect of SFN-related chronic pain is on the structural brain network, and, moreover, to assess whether this effect is different for the genetic variant. To study this, our sample comprised of 20 patients with idiopathic SFN, 11 with a genetic variant of SFN, and 20 healthy controls. For the patients, we also obtained a self-reported maximum pain using a visual analog scale. All subjects underwent 3T MRI imaging, and we acquired a 3D T1 weighted image and a diffusion weighted image using the settings that are displayed on the slide. To pre-process our images, first we used FreeSurfer to define regions of interest, cortical as well as subcortical regions. These are defined from the T1 weighted image. Our diffusion weighted images are subsequently corrected for subject motion and eddy currents. Moreover, they are non-linearly registered to the undistorted T1 weighted image space using Explore DTI. Next, we performed whole brain tractography using constrained spherical deconvolution. To then define the brain network, we used the aforementioned regions of interest as nodes in the network and calculated the tracks between those nodes, those regions. To make sure that our graph analysis is not based on the number of regions that are existing in a certain patient, we made sure that we only compared networks with equal connections, or in other words, that the networks are equally sparse. To quantify our graphs, we used measures of nodal importance. And for this, we calculated the betweenness centrality and the eigenvector centrality, which are both measures of nodal importance. And it's good to note that these measures are not the same as the degree of a node, but they measure how much the node is involved in the network. So it can also be a lower degree node that has the highest nodal importance. For example, the betweenness centrality is defined by the amount of times a certain node is included in the shortest path in the network, and the eigenvector centrality is a relative measure of nodal importance, indicating how many nodes connected to the certain node that have a high nodal importance. And furthermore, we define certain pain-associated regions to check whether the combination of these regions harbor a difference in the idiopathic, the genetic variant of SFN, and the healthy controls. So what we found was that a higher betweenness centrality, so higher nodal importance of the pain-associated regions was found for the genetic group compared to controls, and also for the genetic group compared to the idiopathic group. So it appears that for the genetic group, it's these regions have an increased nodal importance. Interestingly, when we looked at the relation with the visual analog scale for maximum self-reported pain, we found that especially the eigenvector centrality of the pain-associated regions related to the self-reported maximum pain in the genetic group. Moreover, when we added an interaction term to this analysis, we found that the relation between the nodal importance of the pain-associated regions and the VAS score was significantly different for the idiopathic and the genetic group. So, To conclude, we find white matter network differences between the genetic SFN compared to the idiopathic and healthy controls. Previously, in a prior study, there was also a node of higher nodal importance in pain-associated regions, a subject with burning mouth syndrome, so a different type of pain. In the genetic group, we find that the self-reported maximum pain is associated with lower eigenvector centrality of the pain-associated regions, and combined, these two results bring us to the conclusion that there is a distinct structural pain pathway for the genetic group compared to the idiopathic group, which might be indicative of a compensatory mechanism. Thank you very much for your attention. If you have any questions regarding this work, I would be very happy to answer them.